Hello, my name is Caroline G. Long, and I'll be presenting on the topics of nuclear energy and radioactivity in nuclear physics. So, I'm sure you're wondering why I'm dressed as Doc Brown from Back to the Future to give this presentation. Well, like most of us, the only exposure we've ever had to radioactivity has been through movies, which is a good thing. Movies like Tenet, Back to the Future, and so many others shape our understanding of radioactivity and radiation. So, hopefully, at the end of this presentation, you'll have a better understanding of it. I know I definitely did after doing this research. So, let's get into it. I have to turn my video off for a second. Okie dokie. So, nuclear energy, what's the big deal? Like I said, our understanding of it has been shaped by movies. Here's a picture of me and my fiance from this past Halloween, and I'm dressed as Doc and he's dressed as Marty. So, what is nuclear energy? Where does it come from? How do we harvest it? And lastly, why do we care? These are just a few of the questions that I'll be answering today in my presentation. So, the answer to the first question is what is nuclear energy? Well, it comes from nuclear radiation. It also can be referred to as ionizing radiation or decay. Essentially, it refers to energy that's released when subatomic particles are emitted from an atom with high speed. So, there's several different kinds we're going to be speaking about today. The types we're going to speak about are alpha, beta, gamma, and delta. Neutron. I'm sorry. Neutrons are bonus we're discussing today. So each type can be thought of as decay, and they're differentiated by the method of particle emission. So let's dive in. Alpha radiation. That consists of alpha particles that are released in the form of a helium nucleus. If you'll remember from chemistry, that is 2 protons and 2 neutrons together. They are the heaviest, the slowest, the weakest, and the least dangerous form of radiation or decay. But they're also the most ionizing. They are extremely heavy, like I said, and so that causes them to not be able to travel very far from the initial atom. Alpha particles come from the decay of the heaviest radioactive elements such as uranium, radium, or polonium. And even though alpha particles are very energetic, they're so heavy they use up their energy over short distances and are unable to travel very far from the atom. So how can they be stopped? What's their biggest weakness? It's paper. Like I said, they're not very penetrative either. So next, we're going to move on to beta radiation. Beta radiation could be called electron radiation as it consists of free electrons or positrons being emitted from the nucleus. They are smaller than alpha particles because they are a single electron and they carry a single negative charge, whereas alpha particles carry 2 positive charges. They're more penetrative than alpha rays and faster, although it still cannot travel very far from its initial atom. It can penetrate the skin a few centimeters, posing somewhat of an external health risk. However, the main threat is still primarily from internal emission from ingested material. And what is beta's greatest weakness? It's less ionizing and can travel farther than alpha rays, but still not super far. Its biggest weakness is aluminum. Dun, 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 dun. And then we'll discuss gamma rays. You might know this because this is what the Hulk is what turned the Hulk into the big green monster. So, gamma rays are emitted when a highly energetic photon escapes from the nucleus of an atom. And seeing as how they have no charge and mass because they are just short wavelengths and high frequencies. They are also the most penetrative and biologically hazardous of the radiation we'll discuss. They are also weakly ionizing, and this is due, they're weakly ionizing and extremely penetrative. This is due to them not interacting with the surrounding material as strongly as a charged particle would, seeing as how they don't have a charge. And so their biggest weakness is lead. The fourth type of nuclear radiation we will discuss is known as neutron radiation. Neutron radiation consists essentially of the emission of a neutron. It can travel long distances because it doesn't interact with atomic electrons as it has no charge. And it's more penetrative than alpha and beta rays. So now that we know about the basic, what is its weakness? Its weakness is anything that contains hydrogen. So that can be water, plastic, or even concrete. Now that we know about the basic kinds of nuclear radiation, how do we harness it to generate power? Through two processes, one known as fusion, one known as fission. And fission is done by a process known as the Rankine thermodynamic cycle, which we will discuss in a moment. So now let's discuss nuclear fusion. Oops, that is wrong. I'm so sorry. This is nuclear fusion. That's what I meant. Sorry. That's better. Nuclear fusion is the process of nuclei being fused together. It releases several times the amount of power to being fused together, several times the amount of energy generated from fission. However, it requires an exorbitant amount of energy to fuse two positively charged nuclei, and because of their electrostatic forces repelling each other, it becomes difficult to get them to collide. Nuclear fission is a reaction where the nucleus of an atom splits into two or more smaller nuclei, releasing energy. This is the process by which the atomic bombs were engineered as well. So, since more nuclear plants use fission, that is going to be the focus of our presentation, the next half of our presentation. So let's see. Energy is harvested through a process known as the Rankine thermodynamic cycle. And I will outline that as well, but we also have an image in the right corner, and that also will walk you through kind of the graphic of that. So uranium-235 nuclei are hit with the neutron, causing them to split into two smaller nuclei. This fission generates a tremendous amount of energy in the form of heat. This heat then creates steam that runs through a turbine and generates electricity. The steam from that turbine is then cooled in a condenser and pumped back to the heat source in what is referred to as the Rankine thermodynamic cycle. The United States generates more nuclear power in gigawatt hours than any other nation, according to the EPA. So, question, why do we care? Well, we will eventually run out of fossil fuels and we'll need a clean, sustainable alternative, which I believe to be nuclear energy. And here are a few reasons why, according to the National Department, the Energy Department. So, there are three reasons why it does this. Number one is why we should choose it is because it protects air quality. It does not release harmful byproducts the way fossil fuels do. According to the Nuclear Energy Institute, the United States avoided more than 476 million metric tons of carbon dioxide emissions in 2019. That's the equivalent of removing 100 million cars from the road and more than all other clean energy sources combined. It also keeps the air clean by removing thousands of harmful toxins, harmful air pollutants each year that contribute to acid rain, smog, lung cancer, and cardiovascular disease. Second, it has a small land footprint. According to the United States Energy Department, a typical 1,000 megawatt nuclear facility in the United States needs a little more than 1 square mile to operate. The Nuclear Energy Institute says wind farms require 360 times more land area to produce the same amount of electricity, and solar voltaic plants require 75 times more space. To put that in perspective, you would need more than 3 million solar panels to produce the same amount of power as a typical commercial reactor, or more than 430 wind times. Capacitor factor is not included in that calculation. Lastly, because of how dense nuclear fuel is, it takes longer to use, resulting in minimal waste. Nuclear fuel is incredibly dense. It's about 1 million times greater than that of other traditional energy sources. And because of this, the amount of nuclear fuel used is not as big as you might think. All of the nuclear fuel produced by the U.S. nuclear energy industry over the last 60 years could fit on a football field at a depth of less than 10 yards. That waste can also be reprocessed and recycled, although the United States has not yet implemented a program to do so. So that is my presentation on energy and nuclear energy. Let's see for a second. Did I click? All right. And if you have any questions, let me know. And my Works Cited page is right here. And the very last part, I got all my information from the Department of Energy. Thank you.